So, first of all, warm welcome to each and everyone. I'm Eric Krolop, Group Key Account Manager, and I'm delighted to having you with us today for what I hope will be the first of a long series of webinars. Our scope is to share with you our expertise and experience, and we count on your feedback in order to prepare our next rendezvous. We see here the opportunity to foster interactions and exchanges around blasting operation. And by this way, an opportunity to grow together. So do not hesitate to use the chat box for your question, your comment as they come, and we will get back to them later after the presentation. Today, we're gonna try to answer these a bit provocative questions. Bench blasting, am I wasting my money on technology? Our speaker is Javier Munoz. Javier has been working in drilling and blasting business, both in underground and open pit operation for more than 30 years now. He has joined EPC 9 years ago, and after taking very good care of our Spanish operation as general manager, is now our training services manager. And as such, I would say that he participates greatly to the high added value we seek to bring to each of our customers. Already training is at the very core of our business approach. And it is in this context that we want to share with you this series of webinars. So Javier, I leave you the floor.
Okay, well, thank you. Thank you for the introduction. Welcome everybody to this series of webinars that we start today at EPC, and we are very proud to do. We're starting with short technical webinars on drilling and blasting, and we are starting with this one: bench blasting. Am I wasting my money on technology? And hopefully we will give you a nice answer to this question during the next 30 minutes. I think so. Okay, well, we have programmed a series of webinars. Let me see how I can move. Oh, yeah. There we are. Okay, there we go. So we have programmed we have two webinars programmed. The one of today, which is bench blasting, am I wasting my money on technology? And the number two will take place January next year. And we'll be having a look at how energy can be used, or the better use of energy in bench blasting in general. And the question we will be giving an answer is, do you really care about energy in blasting? Okay. So, okay, well, today we'll focus on the basis of good blasting, which is basically controlling the geometry of the face. And we'll be having a look at the state of the art of phase survey, of drilling control, and we'll be giving a couple of examples of audits that we have been doing in the last years that give a good example of cost savings, cost optimization by the only implementation of technology in bench blasting. Okay, so here we go with that. Okay, all of you know that drilling and blasting is the first step in the production chain for mineral production. Okay, in quarry, in mining, and it has a big influence of what is happening afterwards. So a good quality in drilling and blasting is going to affect dramatically what is happening in charging, in hauling, and in crushing and milling. Okay, so these are problems that if I would ask you to give me a list of problems that commonly appear in when bench blasting, I think we will all get to something like that. Okay, we can have fly rocks, which are probably the most dangerous event that we can have in bench blasting. Misfires, toes left after the shot, unstable faces that we have to deal with after that, unsuitable mag pile, a mag pile that is not has not the right shape for our loading machine, so it's too tight, too rough to excavate. The wrong fragmentation for our purpose, so it means usually too coarse, too big fragmentation, but sometimes too fine. And also environmental issues that can be a big issue, big problem for those mineral operations near populated areas. Okay, so these environmental issues can force some mines or quarries even to close down, depending on their location. So big issues. Okay, these technical problems have safety and economic consequences. Okay, that's it. I mean, it's all those problems will be translated into safety and environmental issues that we have seen, vibrations, etc. But they can also be translated into a reduced productivity in the plant in tons per hour, which means that the plant will not be running at a good speed of production. But it can also be translated into costs in energy for the crushing, costs in secondary breaking or blasting, secondary blasting even for dealing with boulders and tows. It's proved, it has been proved many times that a wrong fragmentation, a too big fragmentation will have influence in cost for charging and hauling. Yeah? And but we can also have other sort of problems like mineral reserves loss. For instance, if we are producing too many fines in certain operations, those fines can be a big problem. Okay, we can be putting all that percentage of fines either as an undervalued product or either as something that we have to put into the bin. Okay, we have to discard. Oh, in metallic mining, sorry, we can be having ore dilution, which is a very important issue for this sort of operations. Okay, so I mean, ROM blasting in the end means cost. We have here an extreme example of that. Okay, so quarry blast. So yeah. So basically a big boulder that has been displaced, but okay, so it did go off, but I don't think it went as expected. Well, it's an extreme example, but that gives an idea of what can happen, right? Part of that is explained by the mine-to-mill concept, which says that by increasing your costs in drilling and blasting, which means by drilling more and using more explosives, basically by doing a better use of explosives, by fragmenting more the rock with the chemical energy of explosives, you will be able to reduce your costs downstream in loading, in hauling and crushing, and somewhere we will find a minimum in the cost, and that's the minimum that we have to look for. I do agree with this graph. I mean, it's because the chemical energy is of explosives is the cheapest by far. However, we have to consider that sometimes we do not have to increase our costing in drilling and blasting to find that minimum. Sometimes we only have to do things better. Okay, we sometimes very often by making use of technology, we get to a point where we can make a better use of our explosives, of our drilling. And it's not necessarily that we have to spend more in drilling and blasting to get a better costing on our production. Okay, and that's what we are going to see today. Okay, so the EPC way, we are focused entirely on technology for drilling and blasting, in both in underground and in open pit and quarrying. Okay, so yes, we go quickly to this cycle of use of technology use. We start with a drone survey. Okay, we use a drone for surveying the face, and from that, with photogrammetry, we get a 3D model of the face. We'll see that later on. Using that model, we can design an optimized drilling plan for our purpose, okay, for the fragmentation and heave that we want on the muck pile, okay. That design is transferred to a drill rig, okay, usually fitted with a GPS system, so it will locate precisely on the collars. And very important, we need to control the deviation, as we'll see later, okay. Okay, so once we have the collar positions, once we have the deviation, the real trajectory or deviation of the boreholes, and the 3D model of the face, we are in the position to design the loading plan and the sequencing plan. We do that with our software, the Expertise 3D, same as for the drilling plan, okay. And so we will produce a plan that will, as we will see today and on the next webinar as well, we will produce a plan that will aim for an even distribution of energy within the rock mass. Okay, okay. So that plan is then uploaded to the field tablet, and this field tablet communicates via Wi-Fi with the MEMU, with the mobile manufacturing unit, if we are going to be loading with a MEMU. Important. This tablet has an important mission. Is sometimes we have to be loading hundreds of boreholes. I mean, in quarrying, that might not be the case, but in open pit mining, yes, it is the case. So sometimes it's not unusual to get lost within that field of boreholes. Okay, so that tablet will, which is fitted with a GPS device, will know exactly which borehole we are loading, and it will say so to the MEMU. So the MEMU will be loading the exact amounts of explosives for the precise boreholes. Important. Okay. Okay. The next move is using. We tend to use electronic debts. In this case, we commonly use Devitronic detonators. Okay, that can be programmed very easily, and they can be fired remotely, which is an extra in safety. And as electronic deaths, as you all may know, that gives a very some extra points, especially in precision. So very good tool for blasting engineering. Okay. Okay. Once we have done the shot, we like to pass the drone again. We like to pilot the drone again and do another survey for the muck pile. So we will get data to compare the before and after the blast. That will give us an idea of the muck pile, of the heave of the muck pile, how much we have moved that rock. And from the images taken from the drone, we can even count boulders, so and estimate the fragmentation obtained. So that gives us a sort of feedback on what we have been doing. Okay. Okay, so that's important, and all those data can be stored in our database. Okay, in a database that can be accessible by customers. So every customer can have access to their data, the location of the blast, designs, filming of the blast, because we also use the drones for filming blasts, which is very important. Filming of the blast can give us a lot of information of what is going wrong, what is going right, and all this data can be easily accessible by customers into our database. Okay. Well, this is like a big summary, short summary of what we can do and what we do. But today we're going to focus on the geometrical control of all of this cycle, which is the drone survey, drilling plan, drilling control, and what we can obtain from that. Okay, so let's start with it. Okay. The face geometry. This is the basis for everything. Okay. Knowing the precise geometry of the face is the keystone for any other work, any other job that we want to do with our blasting. Traditionally, the bench has been considered as this, a linear model. Everything is straight, everything is parallel, you know, perfect. And this sort of linear model has been used always for calculating, well, the blast ratio, the amount of explosives, etc. Okay, and the amount of rock that we are going to blast. All that is like the Bible for our costing afterwards. However, as we'll see, this differs quite a lot from the reality. Okay, the reality is more like this. This is a model obtained by photogrammetry of a bench, okay, and of a face to blast. And well, to be honest, it's not too bad. I have seen them much worse than this. But as you can see, nothing is linear there. You have plenty of irregularities on the face, which gives us an idea that reality is not always, well, is never close to the ideal. Okay. What do people usually do to estimate things like bench height, shape of the face? Well, still many people use this nothing. I mean, they just give an eye, just take a look at the face, and they say, well, I think my face is 50 meters high, or it's 12 meters high there and 13 there, etc. Sometimes they make use of a tape, or they make use of a stick together with a tape to make some estimations on the bench height, on the burden in the bottom of the holes, etc. But this is not good enough. I mean, it's very, very, very easy to get errors of more than 1 meter, if not 2, or even more, in the bench height or in the burdens. So, and that can lead to, as we will see later, to cost increase and also to safety issues. Okay, so not good enough. What do we do now? What do we have? What is our the state of the art now is this device. It's a drone. Okay, in the last 2 decades, we have had access to other devices, the lasers. First, we had access to the laser 2D in 2 dimensions that had to be operated manually. Not good enough in precision, but good enough to give us some idea of the burdens in front of every borehole. Then we had the lasers 3D in 3 dimensions that produced a decent model of the face, good enough to start doing designs. However, in the last 5 years or so, we have had access to these drones that produce a model by photogrammetry. So they take pictures of the face, okay, and they produce a drone by from the photographs, okay. Another advantage, well, advantage of this system is it's easy to use, very quick to deploy, and very safe to use as well, because they can be operated from anywhere. I mean, you have to have it from in your vision range, okay. But as you have seen before in the films, the pilot is in a very safe position, having a look at the pictures taken by the drone, okay. So, and on top of that, it's also very precise. You can see the guy there, that's the pilot, and it's very precise. As I was saying, we have been carrying out some tests on precision of these devices, and they are more precise than laser 3Ds. Okay, so very good, all advantages. Yeah? And this is a tool that we use at EPC now for every survey. Okay. Okay, from that we get this 3D model of the face. Okay, this is treated already with Expertise 3D, the software of EPC Group, and that will give us, well, a very good model of the phase that we are going to blast. So no more linear models. Now we are dealing with the reality. Okay, and with that we can start producing safe and productive blast designs. So once we have that model, and with expertise 3D again, we can start producing patterns, drilling patterns. Okay, sometimes these patterns can be complex, especially when we are dealing with multiple rows and with inclined faces. Or so, yeah. What we do here? Well, a nice way to transfer this, because the expertise 3D will give us the color positions for a perfect drilling pattern. The right way to transfer those color positions to the field will be to use a GPS device. Okay, either a manual GPS device, those that you can poles that you can hold yourself, or even better, use drill rigs fitted with a GPS device in the mast. Okay, and as you can see, that's one of our drill rigs in the UK, fitted with that device. Okay, that will ensure that the drill rig will be coloring in the right position all the time. Okay, so we have to drill that. That will take some time, and once it's drilled, very important, we need to control what we have drilled, because as you all may know, it's very common to have deviations, especially, well, depending on ground conditions, on the type of machine that you are using, etc. It won't be unusual to have sometimes big deviations on from the planned drilling. Okay, so marking and coloring errors, that should not be a problem if we are using a GPS device. Maybe we may have a few centimeters, okay, because the drill rig cannot color in the right position. Sometimes it has to move a little bit more, but very little. However, we can, depending on ground conditions and the machine, we can have deflection errors, so deviation, what we usually call deviation. And also the mast might not be set properly. So we could have inclination in both, in any direction, okay, in azimuth or in direction, inclination errors, or hole depth errors as well. Okay, so that's something we have to control, right? As an example, you can see here on the right side of the slide, you can see a front view of a drill plan, and you can see how some boreholes tend to coincide, creating potentially a risk of fly rock at the bottom. But more than that, is creating a potential of boulders and toes left in those boreholes that are separated more than nearly 6 meters. Okay, so we may have problems here. So all that needs to be controlled before producing a right blasting plan. Okay, how do we control this? Well, you may have seen this before. I'm sure you have. We do this by using an electronic probe. The one on the left is the one traditionally used, still being used. It's a pulsar probe, okay, that is being put into the borehole, and every meter that takes the measure of the inclination of the borehole. So afterwards, it reproduces the real direction, the real trajectory of the hole. Okay, nice. However, we have been developing this for the last year. Okay, this is an automatic and user-friendly electronic probe by EPC that, well, operates by itself, okay, and transfers the data automatically to the tablet in the operator's hand. So lighter, easier to operate, and quicker. Okay, nice. Both give a very good result, and they are basic for obtaining a safe, productive design. Okay. So once we have all that, we can say that we have a control. We have control on geometry. Otherwise, as I like to say, if we do not control geometry, we will always have uncontrolled blasting. Okay, no geometry control means uncontrolled blasting all the time. This again, another extreme example of what can happen, but it is a real example. Okay. The most dangerous issue we can have, well, one of the most dangerous issues we can have is fly rock. And you will see here a tremendous real example of fly rocks. Okay. Okay, well. Just a dramatic example of how things can go wrong. Okay. Anyway, well, we won't be having this because hopefully we will be using technology for controlling our geometry, and of course, and on top of that, we will be stopping traffic when blasting near a road or so. So anyway, let's move on. We are going to present now two examples of use of geometry, of use of technology in real cases, and how this use of geometry led to savings in our customer sites. Okay, the first one is in an open pit mine. Okay, and basically we went there. Our technical services went there. They did an audit on the drilling and the design, but basically the geometry of the phases to blast, and they found this. They found that the boreholes near the free phase were having to deal with burdens with in excess of 10 meters very, very often. Okay, 10, 11, 12 meters. The others in the back rows, well, they were dealing with burdens more logical for the drilling diameter. Okay, 3.5, 4 meters. Okay. However, what does this mean? Basically, it means this, as you can see, and this is the blast filmed after that was the design, and this is the blast film. The explosives always tend to work towards the easiest possible way. In this case, the easiest possible way for the front row is upwards, because they have to deal with 11 meters or more. So we're having that. Okay, fly rocks upwards, and as we will see later, the problems mentioned before: boulders, toes left after the blast, etc., which economically means that we have to spend time and money and energy and fuel and people in secondary braking, in secondary blasting sometimes, and well, so it's not good. I mean, all this can be resolved by doing things properly from the start. Okay. So what do we do? Basically, we are going to adapt the drilling plan. Just as you saw before, all the boreholes were vertical, and well, that first vertical drilling, well, we always recommend to incline boreholes for a better work in the toe. But anyway, when you have a face like that, so inclined, you need to adapt your front row, your rows behind as well, and that's what we are doing here. Okay, that can be done manually with the expert here, but it takes time. Imagine that you have to deal with 300 boreholes, okay, or 400 boreholes, which is not uncommon in mining. It can take some time. Okay, so what do we do? Well, we have algorithms included in. I will run the video. Sorry. We have algorithms included in Expertile 3D. So the software can calculate for you automatically the drilling plan once you give it the basic data. Okay, the depth, inclination, the burden, spacing, and so on. Okay. And that will produce automatically a blast drilling pattern. Okay, then you will have to probably make some corrections manually because, well, algorithms are smart, but they are not perfect. But anyway, that saves a lot of time. Okay, a lot of time, and it will reproduce. It will produce a a drilling pattern according to what we want. Okay, so you will see may have to do some corrections, but very little compared to what we were doing before. Okay. Okay, so let's move on. So that was the starting point, the standard pattern. Okay, and as you can see, many boreholes were having to deal with patterns of more than 11 meters. Now we are able to produce patterns much more logical. Okay, and this means a more even distribution of energy within the rock mass that we are going to blast. Okay, when we produce designs that aim this, that look for this, that are searching for a more even distribution of energy, we get results like that. Okay. We not only save time by using the algorithm in the Expertise 3D, but more importantly, we get improved results in terms of safety, but also in production parameters. Okay, like fragmentation, tows, vibrations, etc. Okay. So as you can imagine, having that, those results have nothing to do with having big boulders and toes left after the shot, etc. Okay. Well, that was the first example. We're going to move to the second one, which is in quarrying. And okay, that audit took place in a group of quarries in Europe, and basically they were not using technology. They were estimating the volumes blasted using the famous model, the famous linear model. And okay, as we will see here in this graph, we audited 8 quarries, and 5 out of 8 they were overestimating the volumes by an average of 20%. Okay, which means that they were using explosives and drilling for blasting 20% more than what they were really blasting. Okay, so this very simple. It means that they were increasing their costs by 20%. As simple as that. Okay. What does it mean? Well, it means that the sole implementation of technology, of knowing precisely the shape of your face and the exact position of your holes, in this case, saved 20% of costs like that. Okay, in one go. And I think I could say easily that, because I have some experience now in visiting quarries in different places. Wherever I go, this problem is pretty common. So I won't be surprised to say I won't be very surprised to see something like that in many other quarries elsewhere. Okay, so these things happen very often. You can see out of these 8 quarries, there were 3 quarries that were having the opposite problem. Okay, they were underestimating the volume. So someone could say, well, good for them. They were blasting more volumes with the same explosives, with the same drilling. Well, as we have seen before, and the experience in this audit said so, all the 8 quarries were having problems with wrong fragmentation of boulders or production, etc. So in any case, having excessive burdens is going to lead all the time to poor fragmentation, to tows, etc. Okay, and excessive vibrations as well. So it is not the right economics to play. It's a wrong economy. Okay, so as a summary, the explosives, the drilling must be placed in the right position every time. Okay, at the right burden to the front, to the free face. Part of this misuse of explosives took place in the subdrill, and this is a pretty common error that I see everywhere I go. When technology is not in place, it's very common to overestimate the bench height. hence to subdrill more than necessary. In this case, the average was about 2 meters. 2 meters of subdrill hole I mean, if usually you subdrill 1 meter or so approximately. So this means that they were subdrilling 3 meters, 2 meters in excess. 2 meters in excess of subdrill, hole per hole, blast per blast, means a lot of money. Not only on drilling, but also spent on explosives. And when you are not loading with bulk, but you are loading with cartridges, it means that you are putting your most expensive explosives in the bottom of the hole for doing nothing, just for creating vibrations, which is, I think, in my point of view, this is a big waste of money. Okay, in this case, we estimated that this represented 15% increase in the dig and blast costs alone. The rest was related to the shape of the face that was not as straight as they thought, etc. Okay. Okay, so this is another example of how the implementation of technology in your quarry or mine can lead immediately to cost savings. Okay, you will be able to place your explosives in the right place, and you will be able to use the right amount of explosives, no more, no less. Okay. Right. Okay. Another thing learned from this audit, which was very instructive. This is for the main quarry they had. They were quarries of different sizes, and I think this was the biggest one. The 3D surveys started to be implemented in between 2007 2008, and from that you can see the number of toe holes, holes drilled to deal with toes and etc. Passed to 5,000, around 5,000 to more than 5,000 to nearly none. Okay, it's a transition thing. I mean, things don't change from one day to the next, but by making extensive use of technology, shot after shot, they managed to reduce that amount of toe holes to almost zero in the year 2012. I would like to see the figures of today, of 2020, but I guess it will be none. Okay. So another graph on the right is the drill meters for 2.5 million tons production. Well, again, as they were now, they were able to adapt the drilling pattern and the explosive consumption to the right need of to the right production of rock. For the same reason we have seen before, the drilling meters were reduced by 27% approximately. Okay, so to obtain the same amount of rock, now they drill 27% less drilling and also explosives as well. So not bad. Okay. And again, this is without doing any further improvement in blasting. This is just by saying, okay, let's put the explosives in the right place. Okay. So the question was, am I wasting my money on technology? Well, I would say no. It's no in block capitals letters. No, because the precise knowledge of geometry allow you to optimize your drilling and explosives, as we have seen in these two examples. And for example, as we have seen also, allow you immediately to make less use of secondary blasting and braking. Okay, and more importantly, if you want, that leads you, or that allows you to reproduce successful designs. Okay, once you can control your geometry, you can reproduce designs that gives you what you want in terms of fragmentation, of heave, or whatever. So that can lead you to projects, for nice optimization projects, technical projects like fines reduction. Can I reduce my my percentage of fines after blasting? Well, probably yes. I mean, but you can only do that by knowing precisely where your face is and where your explosives are loaded. Fragmentation control, can I make it thinner? Can I make it bigger? Yeah, I'm sure you can, but again, geometry must be there. Okay, you must control your geometry, or you can look for total optimization cost, like a mine-to-mill project, only with technology. Again, environmental issues like vibrations can be managed precisely with geometry control. As we have seen, excessive burdens lead to high vibrations, and well, if you want to manage your vibration levels, again, geometry is the keystone for that. Okay. So yes, technology in blast design lead to energy control. Of course, the precise knowledge of geometry is the basis for, as we have seen, for any control blast, for any good blast design, any design that aims for safety and productivity. And it's a keystone for the even distribution of energy in the rock mass. Okay. And this leads us to the next question that we're going to ask in the next webinar, which will take place in January 2021, is, do you really care about the explosive energy when designing a shot? Okay. And that's one question we will answer in about 1 month or 6 weeks time. Okay, so that was my presentation. I hope you enjoyed, and we are open to any question that you may have. So I give the word to my colleague, Eric Krolop. Please, Eric, go on.
So thank you, Javier, for this nice and comprehensive presentation. I see no question in the chat box, but maybe somebody would like to react already. So feel free to do so.
Come on, no questions. Don't be shy. Okay, I'm very good at presentations then.
It seems to. Anyway, we will send you, following this this presentation, we will send you an email with our contact details, also a replay of this webinar, and you can have the possibility. We are fully available to go deeper in this discussion with you if you want to. So do not hesitate to contact us in the next days. We will be available. So I see no question. Nobody reacted already. So it's time for us to once again thank you for attending this first webinar. Take care, season's greeting, and see you next time in January. So
yeah, just before you go, just let you know, yes, we insist on the idea that we will give you the recording of this webinar, and we will be sending you a questionnaire to give us feedback, please, if on these webinars, what you think went well, what you think we have to improve. This will serve us to improve our quality of webinars for following occasions, for the next occasions. Thank you all for joining us. It's been a pleasure to hold this webinar, and I hope to see you all in the next one. Okay, so thank you. Cheers.
Bye.
Bye.
Cheers.
Take care.